My name is Sebastian. I shall be dealing with classical mechanics. We'll start with the Lagrangian formulation of classical mechanics. It's an important topic for all competitive exams. NET, JEST or GATE for all exams. Lagrangian mechanics or the Lagrangian formulation of classical mechanics is quite important. Before starting to do problems, of course, we will be focusing more on problems and we won't spend much time on derivations or the basic theories, but I would like to revise some of the basic concepts, some of the basic terminology that we'll be using over and over again. So we start with the idea of a constraint. So constraint as such, it can be seen as a relationship between coordinates of the system, right? It's a relation between the coordinates of the system. It can be an equality, or it could be less than or greater than, something like that. This is just an example for a constraint equation. So constraint equation or a constraint is something that restricts the motion of the system in a particular way. For example, a block sliding along an inclined plane. So essentially, for every particle we need 3 coordinates. To locate a particle in space we need 3 coordinates, and if we have n particles we will need 3n coordinates. Right? But a constraint, the existence of constraint means that all these 3n coordinates are not independent if there are constraints. Because the equations of constraint will relate different coordinates, will be a relation between different coordinates. So all of these may not be independent. So for this reason, using Newton's equations directly to solve an n particle system, problem involving an n particle system, can quickly get complicated. So to avoid this problem, to make all the coordinates independent, what we do is that we introduce a set of coordinates called generalized coordinates. And we generally write them as q1, q2 up to q3n minus k, and we see that there are only 3n minus k independent coordinates, right? Because there are k number of constraint equations, there are k number of relations between the coordinates, so we can only find 3n minus k generalized coordinates or independent coordinates, or 3n minus k degrees of freedom. Right. Now the space spanned by these 3n minus k coordinates, or we can call it as n, small n. The space spanned by these n coordinates is known as the configuration space. So for a single particle, the configuration space is simply 3-dimensional. Right? We need x, y and z. All right. For 2 particles, and if there are no constraints, we will need 3 coordinates for each particle. Right? We need x1, y1, z1 and x2, y2, z2 to locate it in space. Right? So you see that it's 6-dimensional. Now the configuration space is 6-dimensional. You need x1, y1, z1, x2, y2, z2. Right? So you can imagine a 6-dimensional space now. 6-dimensional space. Where each number, in order to locate each point, you need 6 coordinates, or you need 6 numbers. In this case, it's x1, y1, z1 and x2, y2, z2. So here the configuration is 6-dimensional, and each point in this configuration space, we can call it the system point. Each point in this configuration space corresponds to a particular configuration of the entire n particle system. So each point in configuration space represents the system completely. Right? Because in order to specify this point in this 3n minus k dimensional configuration space, you need 3n minus k numbers, or 3n minus k coordinates. All right? And once you specify this point in configuration space called the system point, it completely specifies the configuration of the system. Now we will come to the idea of virtual displacement, which is an idea that we will be using quite often, especially in this what we call as the D'Alembert's principle, or in order to deal with equilibrium. So what's virtual displacement? I shall just explain it by using this example. There are other examples. I will just give you one example. In this case, the constraint is that this block, let's say it's a block of mass m. It's constrained to move along this inclined plane. And the force of constraint in this case is normal to the surface. We write it as Fc vector, the force of constraint. The force that keeps this block along this inclined plane, that's the force of constraint. And you see that it's perpendicular to the surface, it's normal to the surface. So in this case, you see that the constraint itself is changing with time. So initially the constraint or the inclined plane was here, let's say t equal to 0, and at t equal to t1, at time equal to t1, you see that the inclined plane has reached here. Okay, and what's the displacement of this block? The displacement vector of this block, we write it as dr vector. Okay, that's the normal displacement. Okay, you see that this fc vector dot dr vector is not 0. Fc vector dot dr vector is not equal to 0. So in order to, or mainly in order to eliminate the forces of constraint from our formalism, we introduce a new displacement called the virtual displacement, and it's denoted as delta r vector. Okay, so we need to choose delta r vector in such a way that fc dot delta r vector is equal to 0. Okay, so we see that we have to choose delta r vector like this, and if you look at this, this is a possible, okay, it's a possible displacement of the block of mass m here. Okay, it's a possible displacement of the block of mass m, and this displacement is allowed by the constraint. All right, the constraint just says that it has to be on this inclined plane. Okay, so the virtual displacement is a displacement which does not take time. Okay, you can imagine such a displacement. Okay, you are imagining that you are freezing the system for a moment, so the constraint is not changing. So if the constraint is not changing, then the displacement, the constraint itself is not moving, then that displacement is perpendicular, it's orthogonal to the force of constraint. Right, I hope that's clear. In this case, I'll just repeat, in this case, if you freeze the system, okay, or if you assume that the constraints are not changing when you consider the displacement, that displacement is perpendicular to this force of constraint, and then you can have fc dot delta r vector is equal to 0. And this will allow us to eliminate the forces of constraints from the formalism. Okay, so because oftentimes we don't know the forces of constraints, we don't know what the constraint forces are. Okay, the acting on the system, so it's not convenient to have these forces of constraint in our formalism. Okay, I hope that's clear. And this is just one example, but by looking at other examples, we can show that the total work done by the constraint forces, the total virtual work done by the constraint forces always vanishes. Okay, so that's the reason why we take this virtual displacement. This can be called as a virtual work done by the force of constraints. Okay, virtual work done. And we have got this case of static equilibrium. So how do we describe static equilibrium? When we say that a system is in equilibrium, it means that when you say system is in equilibrium, it means that the total forces acting on the system is 0. Let's say the total forces, okay, the vector sum of all the forces acting on the system is equal to 0. That's what we mean by equilibrium, right? But there's a problem here. This is a good equation, right? This is an equation that describes equilibrium. There's a problem here. The problem is that there can be forces that are unknown. Okay, and we cannot really deal with this equation unless we know all the forces, especially the constraint forces. Now, how do we eliminate the constraint forces from this particular equation describing the equilibrium? Okay, so what we do is we simply take dot product with the virtual displacement. Okay, and in this total vector sum of these forces, all the work done, all right, all the force components or the virtual all the constraint force components will vanish because fc dot delta r equal to 0. So we can simply write f vector as the applied force plus the constraint force. Okay, and when we take dot delta r dot virtual displacement, by definition this part becomes 0, and we can write equilibrium in this form. Okay, so you have to note, you have to be careful that summation over fia, this a means applied. Okay, this alone is not 0 because all this delta ri are not independent now. Okay, this is so this is not 0, not equal to 0. All right, but dot delta ri, this is equal to 0. This thing you have to remember. Now, individually, the coefficients of delta ri are not generally 0 because delta ri are not all independent. Okay, that's the idea. Now, D'Alembert's principle is a principle that makes use of this idea of virtual work done, the idea that virtual work done by constraint forces is 0, in order to eliminate the constraint forces from the dynamics. Okay. So he starts with Newton's equation, he rearranges it, okay, Fi minus Pi dot is equal to 0, and then he and what you do is that then you take the scalar, sorry, the dot product with the virtual displacement, okay, and once you do that, you will see that all the constraint forces will be eliminated from the formalism, okay. Now once you have this equation, this is known as the D'Alembert's principle. Once you have this, we can write this delta Ri vector in terms of the generalized coordinates, okay, because delta Ri are not all independent. You can write it in terms of the generalized coordinates using, you will have some transformation equation to go from Cartesian to generalized coordinates, okay. The transformation equations will be generally of this form. All right, and then you make a small rearrangement and all that, and finally you reach this equation. All right. So from the D'Alembert's principle, which is given by this equation, right, we can substitute for the generalized coordinates, make some arrangements, do some algebra, and you can reach this equation. Okay, this is also the equation of motion. Right, and here Qj, okay, this Qj here is known as the components of the generalized force. Right, and it's defined like this. Okay. For some problems, this may be convenient. T here is the kinetic energy. Right? T here is the total kinetic energy of the system. Right? Another way of writing is in terms of the Lagrangian, where L equal to T minus V. Okay. In most of the problems that we are going to deal with, Lagrangian will have this form. It will have the form kinetic energy minus potential energy. V is the potential energy. So you can use either this equation or this equation depending on the situation, depending on the convenience, right, of your problem. All right. So where L equal to T minus V. So these are the Lagrange's equation. And what does Lagrange's equation tells us? It tells us how each of the generalized coordinates evolves with time. Okay. We can solve this, and we need some initial conditions. You can construct this equation and solve it, and then you can find Qi of T and let's say Qi dot of T. All right. So you can find the coordinates, the generalized coordinates, as a function of time. Okay. So essentially, this equation tells you how the system point evolves in the configuration space. All right. So the configuration of the system, initially the configuration is represented by this point, okay, and the configuration actually changes, and the system point evolves in the configuration space, and the Lagrange's equation actually tells you the trajectory the system point will take in the configuration space. Okay. So essentially, you get the evolution of the time evolution of the system. Okay. So the configuration space trajectory can be like this, anything. All right. The configuration changes with time. So this is an example, or this just represented the representation of a trajectory in the configuration space. Okay. Now we can start solving problems. Let's start with the simple case where we talk about the free particle in space using Cartesian coordinates. So we are talking about a single free particle in space, right? So the Cartesian coordinates are x, y, and z. Cartesian coordinates are x, y, and z. These are all independent, so we don't have to look for other generalized coordinates here, all right? And we need to find the Lagrange's equation, all right? The equation that we mentioned earlier, it's known as the Lagrange's equation or the Euler-Lagrange's equation, all right? People call it by different names, but we need to find the Lagrange's equation here. Okay, so we can write the Lagrange's equation in this form. We can write it d by dt of dou t, where t is the kinetic energy, by let's say dou x dot, okay, minus dou t by dou x is equal to, we can write the generalized force component as qx. Right. So here q1 is equal to x, q2 is equal to y, and q3 is equal to z. That's all. Okay. Now we know that we can find kinetic energy. Kinetic energy can always be written in this form: half m x dot square plus y dot square plus z dot square. Right. So you see that dou t by dou x dot becomes mx dot, and dou t by dou x, in this case it's equal to 0. All right. And what else do we have here? If you take d by dt of dou t by dou x dot, you will get mx double dot. Right. So we just need to construct this equation. We have found this part, it's equal to mx double dot. We also need to find qx. Right. So how do we find qx? Since it's a single particle, we don't have a summation here. So qx, it can be written as this means that it's the generalized force component corresponding to the coordinate x. Okay. So qx, you can write it as f vector dot dou r vector by dou x. That was the definition. Okay, if you look at it. Now what's dou r vector by dou x? What's r vector? R vector can be written as x, let's say x I cap plus y j cap plus z k cap. So dou r vector by dou x is simply I cap. Right? That's I cap. So you see that using this qx, okay, you just substitute this back here, okay, and you see that qx is equal to f vector dot I cap. Okay, that's a unit vector along the x-axis. This is the unit vector along the x-axis, and this is nothing but the x component of the force vector. Right? We can write it as fx. Right? Because we can write the force F vector as Fx I cap plus Fy j cap plus Fz k cap. Right? And if you take this is an orthonormal set of basis vectors, this I, j and k. So if you take f dot I, because I dot I is 1, I dot j is 0 and I dot k is also 0, you get fx. Right? So now it's just a matter of putting all this together. You just put all this together and you will get the equation of motion for the x coordinate. We have written it only for the x coordinate here. Right? So you see d by dt of dou t by dou x dot is mx double dot. So you see that mx double dot is equal to fx. Right? Similarly, it's just the same procedure for y and z coordinates. Okay? The good thing about Lagrange's equation is that for each generalized coordinate you have one equation. For each generalized coordinate you have got one equation. Similarly, you will see that my dot equal to fy and mz double dot equal to fz. All right. Now these are nothing but the components, the component form of the Newton's equation. So we are just seeing that the Newton's equation is completely equivalent with the Lagrangian mechanics. Right. So the Newton's equation we would have written mr vector double dot is equal to f vector. Okay, if you write it in component form, you get three equations, one for each component, and that's exactly what we got using the Lagrangian formulation also. Okay, I hope that's clear. Now the next example I would like to discuss is the motion of one particle using plane polar coordinates. Right, using plane polar coordinates. Okay, so here we are being asked to use the plane polar coordinates as the generalized coordinates. What are the plane polar coordinates? Okay. If you look at the coordinate system, you have this particle here, okay, one particle, and the distance from the origin you can write it as r, and this angle is theta. Right? Now r and theta is sufficient to locate this particle in this plane. Okay, you can tell how far it is from the origin, and you can give the angle with respect to the x-axis, and that will completely determine the configuration or the position of this single particle in space. Okay, you can alternatively use x and y. Okay, so the same point can be written in Cartesian coordinates as x comma y or r comma theta using the plane polar coordinates. Okay, now we are supposed to use the plane polar coordinates as the generalized coordinates. Okay, that's it. And this is instructive. We can use the idea that we get from here for many other problems, okay, to solve problems in a quick way. So when plane polar coordinates are involved in later problems, we'll see that there are certain shortcuts that we can take. Okay. But here we'll do it for starting from the very first step. Okay, but later on we can use the shortcut. Right. Okay. So in this case, we can write the transformation equations like this. We know that x equal to r cos theta. Okay, this is x equal to r cos theta, and y is equal to r sin theta. Okay. But we need to find the the kinetic energy. So we have to find x dot equal to minus r. Okay, we can use the product rule. We can first take r dot cos theta, okay, minus r sin theta dot. Okay, you take the derivative with respect to time, you get minus sin theta dot. Okay, and y dot is equal to r dot sin theta plus r cos theta dot. Right? What's the kinetic energy? T is equal to half m x dot square plus y dot square. That's the usual definition for kinetic energy, right? And what do you get? You just square this and add, right? You will see that the kinetic energy becomes half m r dot square plus r square theta dot square, okay? R dot square plus r square theta dot square, or r theta dot whole square, okay? Now you don't have to do all this to reach this step, okay? That's a shortcut I mentioned, right? Because there are two components of velocity. This you can call it as the radial velocity. It may move along the r direction. It can also have we can call it as a tangential velocity, a velocity along the theta direction, all right? What's the velocity along the theta direction? If theta dot is the angular velocity, the corresponding linear velocity would be r theta dot, am I right? Okay, because v is equal to r omega. We are familiar with this, right? So the tangential velocity is r theta dot, right? And the radial velocity is r dot. So the total, the square of the velocity would be r dot square plus r square theta dot square, okay? So you can, without going into these transformation equations, you can directly write this equation just by looking at the system, right? You just have to be careful, all right? So that's that. Now we have got the kinetic energy. Now we need to find the equations of motion, or the Lagrange's equation, okay? So for the Lagrange's equation, what we do is we find dou t by dou x dot, okay? And that's equal to mr dot, all right? And dou t by dou r dot. We have here two generalized coordinates, r and theta. So we have to find one equation for r and one for theta, right? So first let's find the equation for r, the equation of motion for the coordinate r, for the generalized coordinate r, okay? So you see that it's d by dt of dou t by dou r dot minus dou t by dou r is equal to 0. That's the equation for r. We know that. Now we just find dou t by dou r dot, that's equal to mr dot. If you take d by dt, dou r dot is equal to mr double dot. No surprises there, right? But you see that here, unlike in the previous case, dou t by dou r is not equal to 0. You see that dou t by dou r here, it's not equal to 0. What's it? Dou t by dou r is equal to, just take the derivative with respect to r, and you see that it's equal to mr theta dot square. Dou t by dou r is equal to mr theta dot square, all right? Now you also need to find the generalized force components. You need to find generalized force components. So let's have it here, right? Let's remember this. We have got the first term, that's mr double dot. The second term is mr theta dot square, okay? Mr theta dot square. Let's find the generalized force components, okay? In order to find the right hand side of the equation, all right? So we can write the generalized force components as qr and q theta, okay? qr and q theta. So what's qr? By definition, because it's a single particle, you don't have a summation. So by definition, qr is equal to f vector dot dou r vector by dou r, okay? This is r vector and this is r. Dou r vector by dou r. Now how do you find dou r vector by dou r, right? Dou r vector by dou r. How do we find this, okay? We notice that dr vector can be written in this way, okay? We need to find this. So if you look at dr vector, okay, we know that it's a displacement, right? And we are writing it in terms of the displacement in the theta direction and the displacement in the r direction, all right? So displacement in the r direction is simply dr, right? This is a distance. This is a displacement along the r direction or r cap direction, all right? So, or we can call it as a radial displacement. You can call it as the radial displacement, okay? What's the tangential displacement? What would be the tangential displacement? Okay, if you look at this like this, if the angle changes by d theta and this is r, okay, we see that the displacement, it has to be a length, okay? The tangential displacement is what? It is r d theta, right? So this is the theta cap direction, this is the theta cap direction. So displacement along the theta cap direction is not d theta, it is r d theta, right? So this you can write as r d theta theta cap. Okay. Now dr vector can also be written in this form, because this we can write as equation 1, and r vector is a function of r and theta. Alright. So you can write dr vector also using the chain rule. That would be dou r vector by dou r dr. That's a chain rule. Alright. If you have got f of x comma y, for example, okay, and you want to find df, okay, if we get f is equal to f of x comma y, this is known as the chain rule. If you want to find df, you find dou f by dou x dx, right, plus dou f by dou y dy. That's all. That's the same thing that we are, it's the same thing we are doing here. Okay, so dou r vector by dou r dr plus dou r vector by dou theta d theta. So you see that both equation 1 and 2 are expressions for dr vector, right? So you can just equate the coefficients of dr here, and you see that dou r vector by dou r is equal to, you just equate it here, right? So the coefficient of dr is r cap here, here it's dou r vector by dou r. So dou r vector by dou r is equal to r cap, okay, and dou r vector by dou theta, this thing here, the coefficient of d theta. The coefficient of d theta here is r theta cap, okay, is equal to r theta cap. Now we can use it here. So you see that qr is equal to f dot dou r vector by dou r, that's equal to f dot r cap. What's f dot r cap? It's just the component of the force along the r cap direction. We can simply write it as fr, right? qr we can write it as fr. Alright, so this allows us to find, so qr is equal to fr, so this allows us to find the equation of motion along the r direction. Alright, you just combine all these things, you see that d by dt of dou t by dou r dot is mr double dot minus mr minus dou t by dou r, so it's minus mr theta dot square is equal to fr. Okay, that's the radial force. The radial force. Okay, you will notice that this is the what we call as a centripetal force, or the centripetal component of the force. Okay, this is simply the centripetal force. Okay, you can just look at it and convince yourself that this is the centripetal force. So the total force along the r direction, along the radial direction, it is mr double dot, and there is also a contribution from the centripetal force. Alright. So that's the first equation. That's the equation of motion for r. I hope that's clear. Okay, we started with this. We found the kinetic energy in terms of r dot and theta dot. That's this. Okay. We found all these things and equated it with qr. Right. D by dt of dou t by dou r dot minus dou t by dou r is equal to qr, the r component of the force, and that's simply fr. Okay, the component of force along the r direction, or the radial direction, the component of the force along the radial direction. Okay, so we have got the equation of motion for the coordinate r. Let's find the equation of motion for the coordinate theta. Okay. So we have got t is equal to, I'll just write it again here, half m r dot square plus r square theta dot square. Is that correct? Yes. Now, what's dou t by dou theta dot? Dou t by dou theta dot here is mr square. Okay, that's mr square theta dot, right? Mr square theta dot, and you see that in this case dou t by dou theta is equal to 0. There's no theta dependence here. Okay, so one thing that I want you to keep in your mind is that you can treat q and q dot as independent. Alright, in the Lagrangian formulation, we can treat q and q dot as independent. Alright, so if you have a q, the derivative with respect to the partial derivative with respect to q dot will be 0. If you have a q dot alone, the partial derivative with respect to q will be equal to 0. Okay, so you see that here dou t by dou theta is equal to 0. And what is d by dt of dou t by dou theta dot is equal to mr square theta double dot. That's not all. You have to be very careful because r is also time dependent. You also have one more term. Okay, you have to use the product rule here. You have got one more term. That's mr square theta double dot plus you also need to take the derivative of r square with respect to time, so it becomes 2mr and r dot theta dot, right? We have got this. Okay, and what's f theta? F theta, this is equal to f vector dot dou r vector by dou theta. Okay, and what's dou r vector by dou theta is r theta cap, so it is f vector dot r theta cap, and f vector dot theta cap we can call it as f theta, the tangential component of the force. Okay, so you can write as f theta, and we have got this r here, so it's r f theta. It's r f theta. You might notice that this is the torque. All right, this is the equation for the torque. All right. Now you just substitute it all together, and we'll get the final equation. Okay, the equation of motion for theta becomes, I'll just write it here. You combine this, we have got this here and this here, so you just combine and you get mr square theta double dot, mr square theta double dot plus 2m r dot theta dot is equal to r f theta. Okay, r f theta. All right, and yeah, that's it. Okay. Or if you just look here, you can also write this term like this, d by dt of dou t by dou theta dot, right? It's instructive, look at it in a slightly different form. Okay, here we have expanded this dou t by dou theta dot, but otherwise we can write this as d by dt of dou t by dou theta dot. Okay, it acts only on this term, dou t by dou theta dot, so that would be, that would be mr square theta dot. Okay, this is dou t by dou theta dot, right, is equal to r f theta. Right? And you will notice that this is the angular momentum L. So what the equation that we have here is dl by dt is equal to r f theta. The rate of change of angular momentum, okay, is equal to the torque acting on the system, the external torque on the system. Okay, that's the equation that we have here, right? Okay, so that's how we do these problems. First we have to finalize what generalized coordinates we are going to use, and then just follow the machinery. All right, it's you can do it rather mindlessly, it's just calculations. All right, in Newton's, if you had to solve a problem using Newton's equations, it gets complicated. You have to take care of all the forces and their directions. You have to really look at the physics of it. Okay, but here we have a well-defined process. Okay? Here we have a well-defined process. The process goes like this. Here we have got a well-defined process, and the process goes like this. Okay. So first thing you need to find is the kinetic energy. In most problems we'll do with the Lagrangian. All right. We need to find the kinetic energy. That's equal to half m x dot square plus y dot square plus z dot square. That's for single particle, right? If you have a number of particles, then we can write it as simply half m. If number of particles, different masses, say, so you can write as half summation over I mi ri dot square, ri dot square. That's the kinetic energy. Okay. You also need the potential energy. You can construct. You can find L equal to T minus V. Okay, that's just a scalar quantity. You don't have to worry about the directions of forces, etc. Just construct the scalar quantity called the Lagrangian. Okay. Now, once you finalize the generalized coordinates, you write this in terms of the generalized coordinates. All right. You write the kinetic energy in terms of the generalized coordinates. You write the potential energy in terms of the generalized coordinates. Construct the Lagrangian, and then just mindlessly apply the equations. Okay. I mean, it's quite easy. It's just it's very easy when compared to the Newton's formalism. All right. Some cases, as I said, it's convenient to use the generalized force, but you don't have to use the generalized force. You can always use this form. All right. You can always use d by dt of dou L by dou Q I dot minus dou L by dou Q I is equal to 0. This can be used. Okay. Alright, the Lagrangian need not always have the form t minus v, etc., but that's another problem. Most of the problems that we deal in this syllabus, at least in the master's level classical mechanics, most of the problems involves the Lagrangians of the form t minus v. Okay, there are exceptions. You will see these exceptions as we go on. Okay. Well, let's solve another interesting problem. It's called the Atwood's machine. Atwood's machine. So you have got two masses, m1 and m2, and a pulley here. All right. So the total length of the string is L. The constraint is that the length of the string remains the same. Okay, it's non-extensible string. Okay, so the constraint is, okay, the string is non-extensible. Non-extensible. Okay. So you see that generally we would need, so this is on a plane, all right. So generally we would need, so this is just, it has only one movement in one dimension, right? It has only movement in one dimension. So generally we would need one coordinate for this and another one for this. Okay, the height. Okay, we can call this as x1 and this as x2. Right? We can call this as x1 and x2. All right. Okay, but the constraint says that both these are not independent. Okay, if you take this distance as x1 to mention the position of m1, okay, and x2 as position as the distance or as the coordinate to specify the position of m2. All right. All right. Now, if you do that, the constraint says that both these are not independent because x1 plus x2 has to be equal to the length of the string. Okay. This means that you don't have to use x1 and x2, two different independent coordinates. You cannot use two independent coordinates. We can just use x here. We can just use x here. Okay, and the other one has to be L minus x. The other one has to be L minus x. Okay, so that's what we have noted here. This distance is x and this has to be L minus x. So there's only one generalized coordinates. One generalized coordinate. Okay, and that is x. So we have chosen the generalized coordinates. We have chosen the generalized coordinates. What's the next step? The next step is to find the, let's say we can find the kinetic energy first. The kinetic energy. T is equal to, you can write it as half, okay, m1 x dot square, that's the kinetic energy of this particle, all right, plus half m2, right, what's the coordinate of this? So we can say half m2 L minus x, okay, with the corresponding velocity. I'll just write it for the sake of clarity, d by dt of L minus x square, right? But you see that d by dt of L is 0. This is the velocity, okay, corresponding to L minus x, rate of change of L minus x, that's the velocity. So this simply becomes half m1 x dot square plus half m2 x dot square. The minus goes because when you do a square, the minus disappears. All right. So the kinetic energy we have already found, T equal to half m1 plus m2 x dot square. That's the kinetic energy. What about the potential energy? What about the potential energy? All right. So when you write the potential energy, the thing you have to be careful about is the reference point. All right. Sometimes you can choose reference points in such a way that the problem becomes very simple. So because only the difference in potential energy between 2 points is physical, all right, only the potential difference is physical, you can always choose the reference point, the zero of the potential energy at your will, all right, as you like it. Okay. So in this case, we can take the reference point. The convenient choice of the reference point is to take this as the what do you say, the zero of the potential energy. This line as the zero of the potential energy. Okay. So above this, if you go above this, the potential energy will be positive, and if you go below, the potential energy will be negative. All right. Once you do that, once you choose the reference point, the reference line, we can write V is equal to. Now you should know that choice of reference point does not reflect in your final result. All right. Whatever reference point you choose, if you do it consistently, you will get the same result in the end. All right. The equations will not change. This is easy to show. But the problem, the calculation can become quite simple by choosing the reference points wisely, okay, carefully. We'll see that. So here V becomes, it is let's say minus m1 gx, am I right? It's minus m1 gx because this is 0, so above is positive, below is negative. Okay, so how much has it gone from the 0 of the potential energy, that is minus m1 gx, and minus m2, what is the distance? It's L minus x, or I can write it as minus m1 gx plus, there's a g here, right, because mgx is the potential, mgh is the potential energy, you know that. So this is minus, so this is minus m2 gl plus m2 gx. Okay, that's the potential energy. Now the next step, as I said, is to construct the Lagrangian L equal to t minus v. Okay, so this is not quite difficult. This is quite easy. If you practice a few problems, you will see that sometimes there are tricks that will give you, there are shortcuts that gives you the Lagrangian immediately, right? But we can always do this. We can always write the Cartesian coordinates, write the transformation equations, find the kinetic energy, find the potential energy, and t minus v. Okay, write them in terms of the generalized coordinates, and you have the Lagrangian. What's the Lagrangian? L equal to t minus v, that's equal to half m1 plus m2 x dot square, okay, plus m1 gx, right, plus m2 gl. We don't have enough space here. Let's go to the next page. I'll write it here, okay, so that it's easier. So L equal to t minus v, that's equal to half m1 plus m2 x dot square. Okay, we can just write it. So since it's a minus, t minus v, this becomes plus m1 gx. You can just write from here, right, plus m2gl minus x. Okay, you see that there's a minus sign here. Now there's just one coordinate. You find dou L by dou x dot. Okay, and dou L by dou x dot, as I said, it's the easy way. This is quite easy to do. Just find dou L by dou x dot. Okay, that's a partial derivative, and it's equal to m1 plus m2 x dot. Okay, just find the derivative with respect to x dot, right? So it becomes m1 plus m2 x dot. Okay, and what's dou L by dou x? Dou L by dou x becomes, okay, it is m1 minus m2 g. Okay. So if you see here, if you can look at it in, you can look at it here. So if you take the derivative dou L by dou x, you will have an m1 g from here and minus m2 g from here, because there's a minus sign here. All right, so that's why we have got m1 minus m2 g. Okay, now the Lagrange's equation, the equation of motion, is simply this: d by dt of dou L by dou x dot minus dou L by dou x is equal to 0. Okay, that means m1 plus m2 x double dot, right, taking derivative with respect to time, minus m1 minus m2 g is equal to 0, or we can rearrange this and find x double dot, right? You see that x double dot is equal to m1 minus m2 divided by m1 plus m2 g, right? So we have solved the problem without any information regarding the what do you say, the strength, or the what is the tension, the string tension of the string. All right, so we solved this problem entirely without, and nowhere in our formulation we had to involve a force of constraint or the string tension or anything like that. Okay, now if you have solved the same problem using Newton's equation, you will appreciate how easy this is. Okay, and such problems can be easily done. Now we can, so these are the standard examples. We discussed free particle in space, free particle using plane polar coordinates. We also did, what do you say, the Atwood's machine, and there can be different kinds of Atwood's machine. All right, this is the simplest case, and there can be different formulation or different configurations of this masses with the number of pulleys, and always you can, if you are careful enough, it's not very difficult to solve it using the Lagrange's formulation. This is the simplest case of Atwood's machine. We can do another one or two more problems, including with some other configuration of masses and pulleys. Okay. Now this is another standard problem, the simple pendulum. The simple pendulum. So again, you need to find the equation of motion. All right. You see that there are generally, if it's simply a bob of the simple pendulum, you would need two coordinates, x and y, right, x and y. But you see that they are not all independent, because the length of the string, okay, the length of the simple pendulum remains the same, which means that the constraint is x square plus y square is equal to L square. Okay. This means if you know x, you also know y, so they are not independent. You need only one generalized coordinates, and the convenient choice of generalized coordinates is the angle theta. Okay, you just need to say the angle theta, or at what inclination the simple pendulum is with the y-axis, then you know the complete configuration of the simple pendulum. So you need only one generalized coordinate, and in this case the convenient choice is theta. You don't need x and y, you just need theta. All right. Now, as I said, you can find the kinetic energy. Okay. Or first we can write down the transformation equations. You see that x equal to, in this case, okay, x equal to L sine theta and y is equal to L cos theta. You can find x dot, you can find y dot, right? Find x dot, find y dot, and you find t equal to half m x dot square plus y dot square, and you will see that the kinetic energy is, okay, the equation for the kinetic energy is half m L square theta dot square. That's it, right? Now, I did not do all these steps because there is an easier way to do this. All right. You see that the kinetic energy, it has only one component of velocity. Okay. Since the length does not change, the radial velocity term is not there. This movement is not allowed. Right. This movement is not allowed. So there is no radial velocity. There is only the tangential velocity. There is only the tangential velocity. Okay. So what's the tangential velocity? The only component of velocity that we have is, you know, that is L theta dot. L theta dot, just like V is equal to R omega. All right. V is equal to L theta dot. All right. And the kinetic energy is half mv square, and that's equal to half m L square theta dot square. Okay. So you don't have to do all these transformation equations. You can do it if you like, but you don't have to do it. In this case, it's easy. Okay. We can start with this expression t is equal to half ml square theta dot square. Okay. There's no problem there. Okay. I hope that's clear. No difficulty. Okay. We have got the kinetic energy now. What about the potential energy? Again, you can find, so in order to find the potential energy, you can choose at least two different, you can choose any reference point, or two possible choices are, you can choose the reference point as this one, you can take this as the zero potential, or you can take this as the zero potential. All right, both works. You can convince yourself that both works, and I will take this as the reference point. This will be the zero potential energy. Okay, this as the reference point. So the potential energy is determined how far what's the distance of the bob of the simple pendulum from the reference point. Right. So that's simply y. So we see that V is equal to minus mg y. Okay, because mgh, that's mgh, right? And you see that y is equal to, because we cannot use y, we are using theta as the generalized coordinate, so you write it as minus mg cos theta. Okay, mg L cos theta, because y is equal to L cos theta. This is the potential energy. Now we have got the Lagrangian L equal to t minus v, that's equal to half m L square theta dot square plus mg L cos theta. Okay. Now it's just a matter of finding the equations of motion. There is only one generalized coordinate, so you have one equation of motion, one Lagrange's equation, and you see that you can find it easily. You see that d by dt of dou L by dou theta dot minus dou L by dou theta is equal to 0. That's the equation of motion. Right? And what's dou L by dou theta dot? It's equal to dou L by dou theta dot is equal to, you just take the derivative with respect to theta dot, you see that is equal to ml square theta dot. Okay, this is the Lagrangian, and d by dt, if you take d by dt of dou L by dou theta dot, since L is a constant, right? L is a constant, this becomes ml square theta double dot. Okay, you also have dou L by dou theta, you also have to find dou L by dou theta, and you see that since L, I'll just write L here again, L equal to half m L square theta dot square plus mgl cos theta. Okay, so dou L by dou theta is equal to mgl cos theta. Derivative of cos theta is minus sin theta, so it's sin theta, and you have got a minus sign here. Okay, now it's just the equation of motion becomes, okay, you can write as d by dt of ml square theta dot, okay, is equal to, since there's a minus sign here, we can write as, yeah, this is equal to dou L by dou theta, so it's equal to minus mgl sin theta, and often we are interested in the theta double dot. Okay, so you can solve for theta double dot from here, and this is that theta double dot is equal to, or we can write this equation, theta double dot plus g by L sin theta is equal to 0. Okay, now this is the required equation describing the motion of the simple pendulum. Right. So this, if you can solve this equation, once you get the initial theta and initial theta dot, you can solve this equation. Okay, and you can find theta of t. Okay, what would be the angle given the initial position and velocity of the bob of the simple pendulum, or given the initial angular velocity and position of the simple pendulum, right? The angular orientation and position, sorry, the angle and the angular velocity of the simple pendulum. Okay, you can easily find out the equation of motion describing equation of motion for the simple pendulum. Okay, okay, good. Now we can go on to next problem, that's of the linear harmonic oscillator. Okay, linear harmonic oscillator. So the linear harmonic oscillator is, again, it looks like a simple pendulum. You see that the equation looks like a simple pendulum. Okay, the only thing you need to remember is that v is equal to half kx square. There's only one degree of freedom. We can take it as x. It moves along the x-axis. Right. So we can take v is equal to half kx, or we can find, because f equal to minus kx for a spring, f equal to minus kx. So you can find the potential energy from here, or you can use this information that v is equal to half kx square for a linear harmonic oscillator, where k is called the spring constant. Okay, this is called as the spring constant. You see that this is quite easy. Okay, this is quite easy because the kinetic energy is half mx dot square. The kinetic energy is half mx dot square. Okay. All right, and what's potential energy? That's equal to half kx square. Right, and what's the Lagrangian? L equal to t minus v, that's equal to half mx dot square minus half kx square. Fine. Now we find dou L by dou x dot, you get mx dot, and if you take d by dt, you'll get mx double dot, and dou L by dou x is equal to minus half kx. Right, just combine this and write the equation of motion as, you get mx double dot, you take d by dt of this, okay, plus, because it's minus dou L by dou x, no, sorry, dou L by dou x is minus kx. Okay, the half is gone because there's a square here. Okay, I'm sorry about that. So dou L by dou x is minus kx, so mx double dot plus kx is equal to 0. That's the equation. That's the equation of motion. Again, you can, if you know the initial conditions, x and x dot, okay, you can solve this equation and find x of t and x dot of t. Right, so given the state at any time, given the configuration at any time, this equation will allow you to find the configuration at any other time, the position and velocity at any other time. Okay, all right, and we can also write it in this form. Okay, it's often written as x double dot plus k by m x equal to 0. Okay, and this is often compared with the form x double dot plus omega square x equal to 0. Right, so this omega for this the omega for this spring can be written as square root of k by m. Okay, that's also an important result that we might be using in some of the problems. Okay, all right. It's known as the angular frequency. Okay, this omega is known as the angular frequency. Okay, angular frequency. Angular frequency, right? Okay, that's it. So that's an easy problem. Such problems, there are many problems being asked in the net exam, especially CSIR net exam, using a spring and a mass, or using two springs and masses. Okay, this is the starting point of doing such problems. And so you remember, you have to be careful here, the x here, okay, you have to understand this x, it is the, you can take it as the displacement from the equilibrium position. It's a displacement from the equilibrium position, right? It's a displacement from the equilibrium position. So in this case, it doesn't really matter, but some cases you have to be careful, all right? You can, if you take the equilibrium position as x0, then the generalized coordinates, okay, the displacement, you can write x prime is equal to x0 plus x, okay, or x equal to x0 plus x prime, where x prime is the displacement. Okay, it's the displacement. So in some problems we have to be careful. In this problem it doesn't matter. We get because the differs only by a constant. It does not really change your equations of motion. Okay. All right. We can go to the next problem. It's a spring pendulum. It's a combination of the two problems that we discussed earlier. Okay, it's called a spring pendulum. Okay. Now in this case we will have be a little bit more careful. We discussed a simple pendulum. We discussed a simple pendulum. Okay. We discussed linear harmonic oscillator. Now this is just a combination of it. Right. So it seems complicated, but you will see that the Lagrangian method, in the Lagrangian method you can solve it quite easily. Right, so we have got the spring pendulum. Instead of the string, okay, instead of the string here, you will have a spring. That's all. That is all. Okay, and this L, all right, here L, we'll call it as the equilibrium length. Equilibrium length. Okay, so the x is the elongation of the spring. X here is the elongation of the spring. All right, how much it has elongated from the equilibrium position. Okay, equilibrium length. Okay, this thing here, it's important to write it in this form. We cannot simply write it as x. Okay, it has to be L plus x because L is the equilibrium length. Now in the previous problem also you should have actually written it as L plus x, where and only x would contribute to the potential energy. All right, in the previous problem also we could actually have written it as L plus x. Okay, L plus x, where L is the equilibrium length. Okay, but this L does not appear in the kinetic energy because when you take the time derivative, this disappears, and the potential energy is involved. Potential energy only involves half k x square, the elongation, how much it has elongated from the equilibrium position. Okay, so at L, if the length of the spring is L, the potential energy is 0. Okay, that was the assumption that we took, or that's the reference that we took in the previous problem. Okay, that assumption is there. All right, we have assumed, or we have taken the reference potential energy, or the zero potential energy as corresponding to the length L. Right, and the elongation is x, and then it all works. Right, so this implicit idea was there, but here we state it more clearly. L is the equilibrium length, and this we can write as L plus x. And what's the kinetic energy? We can write, of course, the transformation equations and all that, but we know better than that. T is equal to half m. If you remember, for spring pendulum it was half m L square theta dot square. Am I right? Because it only had a tangential velocity. The length of the string would not change for a simple pendulum. Okay, here it will have a tangential component as well as a radial component, because it also moves in this direction. All right, it will have a tangential component as well as a radial component. All right, so you have to be a bit more careful. It's half m. What's the radial component? It's simply x dot square, because L is a constant. All right, it's x dot square. Okay, what's the tangential component? It is L plus x whole square theta dot square. Okay, L plus x whole square theta dot square. So we need here two generalized coordinates. We choose them as theta and x. These are generalized coordinates we choose. Okay, theta will tell you this angle at which this thing is, and this x would tell you at what elongation the spring is, and together that's enough to completely specify the configuration, okay, or the state of the simple pendulum. All right, I hope this is clear. This is simply what the generalization of what we wrote as L square theta dot square. Okay, here the radius is L plus x, so you'll have L plus x whole square theta dot square. So if you notice, this is exactly the same thing that we wrote for plane polar coordinates. If you remember, we wrote the kinetic energy in case of plane polar coordinates as half m r dot square plus r square theta dot square, if you remember it, right? And instead of this r, you have got L plus x here. Okay, instead of r, you have got L plus x here. Okay. So that's T, and what's V? The potential energy. Since it's an energy, you can just write it as sum of all the energies. All right. So there are two contributions to potential energy. One is the gravitational potential energy, and the other one is the spring. The potential energy of the spring. Okay. So you can write V is equal. Again, we'll choose this as the reference point. Right. You can choose this as the reference point. So V becomes it depends on x and theta. We have to write it in terms of x and theta because x and theta are our generalized coordinates. So V of x comma theta becomes minus mg, this height, right? This height minus mgh. Okay, because this is 0, it becomes minus. So minus mg, and what's this height? It's mg L plus x cos theta. Okay, and that's only the gravitational part. What's the part due to spring? Okay, the spring force. Okay, what's the potential energy due to spring force? You know it is half kx square, right? So we write it as half k x square. Okay, this x tells us how much it has elongated from the equilibrium length. Okay, so this is the potential energy. You see that it may look complicated in the beginning, all right? When you start the problem, it may look rather complicated, but it's quite easy. You can do it rather mindlessly. You don't need to imagine, oh, what happens to a spring when it is being elongated, what are the forces acting there. You don't have to imagine all these things. You can just apply this machinery, all right? It's just a set of rules that you can apply. You write the kinetic energy, total kinetic energy, that's a scalar quantity. You can easily write it, write the total potential energy. Now you write L equal to T minus V, okay? And that's equal to half m x dot square plus L plus x square theta dot square, okay? And here there's a minus sign, so it becomes plus mg L plus x cos theta minus half kx square. Again, this may look complicated to you, but you don't have to worry about it. You first find the equation for x and then find the equation for theta. Okay, you can find them independently, and they involve only partial derivative with respect to x and theta, or x dot theta dot. Okay, so it's quite easy to do. You can just do that, and the final equation would be, you just do this. Okay, find dou L by dou x dot. You see that dou L by dou x dot is equal to right, dou L by dou x dot. Okay, I'll just write down the final equation. Okay. So you can find dou L by dou x dot. Okay, you can find dou L by dou x, and you can write down the equation. Okay, we have done the calculation explicitly in the previous cases. You find d by this is the equation for x, d by dt of dou L by dou x dot minus dou L by dou x is equal to 0. Okay, and you see that this gives you can just try that. Okay, mx double dot is equal to m L plus x theta dot square plus mg cos theta minus kx. Okay, that's the equation of motion for x. That's equation of motion for x. Okay. That's correct. Okay, now you just try it. Okay, try the calculation at home when in your free time. Okay, that's not very difficult. Now we can also find the equation of motion for theta. Okay, that's simply d by dt of dou L by dou theta dot minus dou L by dou theta is equal to 0, and that equation becomes, you can do this and simplify, and I'll give you the final result. It's my m L plus x theta double dot plus 2 m x dot theta dot is equal to minus mg sine theta. Okay, you can do that. Okay. So again, doing this is not the difficult part. The difficult part in most cases is to identify the correct generalized coordinates, all right, the most convenient generalized coordinates. And sometimes you also need to fix the reference point with respect to which you calculate the potential energy. Okay, these are the things you have to be careful about. Once you specify the generalized coordinates and write down the Lagrangian, the rest is just mathematical calculations. Okay. Here let's do another problem. The principle of virtual work. We can solve, this is a problem that you need to solve using principle of virtual work. Alright, we'll need to use the condition for equilibrium. So this is the question. A light inextensible string with a mass m at one end passes over a pulley at a distance a. Okay, at a distance a. Right, so this is the situation. This is the light inextensible string. It's inextensible with mass m at one end. You've got mass m at one end. It passes over through a pulley. Okay, at a distance a from a vertically fixed rod. This is a vertically fixed rod, and this distance is a. The other end of a string is a ring of mass m. You've got a ring here of mass m, where capital M is greater than small m, okay, which slides smoothly on the vertical rod as shown. So this slides smoothly on this vertical rod and it reaches an equilibrium. That's what's happening. The ring is released from rest at the same level as the ring is released from the string as the same level as the point from which the pulley hangs. Okay, you release the ring from here. Okay, and it attains an equilibrium. If b is the maximum distance the ring will fall, determine b using the principle of virtual work. Okay, determine b using the principle of virtual work. Okay, that's the question. You need to determine b using the principle of virtual work. Okay, what's the principle of virtual work? Just let's start by writing down the principle of virtual work. Okay, what does the principle of virtual work say? It says that summation over I Fi applied, okay, dot delta Ri is equal to 0. Right. So here you see that the forces are mg and small mg. The forces of mg and small mg. So theta is 0, and when you take the dot product, you just have to multiply them. Okay. So if you write this sum like this, here there is a force mg. Okay, and the virtual displacement corresponding to this we can write as delta x. Mg delta x. Okay, this is because Fi, summation over I Fi applied dot delta Ri. Okay, so this is the virtual displacement of this mass capital M. Okay, and plus the virtual displacement of this mass we will write as delta b. We will write the virtual displacement of this mass, the ring, as delta b. So that is mg delta b is equal to 0. That's the principle of virtual work. That's what the principle of virtual work says. Okay. The important point is that now they are not independent. Delta x and delta b are not independent. Only one of them is sufficient. Okay. How are they connected? How are they connected? What's the constraint that connects them? The constraint is that this is an inextensible string. This is an inextensible string, which means that you can write. We can write the total length of the string is a constant. Okay, the total length of the string, we start from here, it's x. Okay, x plus this length. Okay, that's a constant. What's this length? We are given a here and b. All right, so this is square root of a square plus b square. Am I right? So you see that x plus square root of a square plus b square is equal to L. Okay, that's fine. That's equal to L. Right? From this we can write delta x in terms of delta b. You take delta on both sides. Okay, you take delta on both sides. We know that the virtual displacement, it works just like a derivative. Okay, in most cases it works just like a derivative. It follows the rules of a derivative, except when time appears, then it's slightly different. All right, so because it does not involve time, so the derivative, the time terms will disappear, etc. But here we don't have to worry about that. So you take delta on both sides. So you see that delta x plus, it acts like a derivative, so it's 1 by 2 square root of a square plus b square, and here you have got, you take the delta of b square, it becomes 2b delta b is equal to 0 because delta is L is 0. Okay, so you see that from here you can solve for delta b or delta x. Okay, you can solve for delta x, and you see that delta x is equal to, you solve for delta x, you get delta x in terms of delta b. Okay, that's minus b a square plus b square whole raised to minus 1 by 2 delta b. Okay, you just take it to the other side. Okay, minus, yeah, there's a b here. Okay, so delta x equal to minus b a square plus b square whole raised to minus 1 by 2. This square root of a, this 1 by square root of a square plus b square I have written as a square plus b square whole raised to minus 1 by 2, and thus delta b. Now you substitute delta x in terms of delta b. Okay, now you can pull out delta b and then equate whatever is inside to 0. That's what we are going to do. Right, we have got delta x here. Just substitute this delta x in this and you will get the equation. Okay, just substitute it and rearrange. You will get mg b a square plus b square whole raised to minus 1 by 2 delta b is equal to minus mg delta b. Okay, just substitute it here. That's all. Just directly substitute. Now you solve for, now this delta b is arbitrary, all right? This delta b is common here. So whatever is multiplied by delta b has to vanish. Okay, you can bring this together. Multiplied by delta b is equal to 0. That means whatever is multiplied by delta b has to be equal to 0, because delta b is not 0. Okay, we cannot take delta b as 0. I hope that's clear. Now since delta b is arbitrary, whatever is multiplying them has to be equal to 0. Okay, now you can use that to solve for b, and the final answer you will see that b square is equal to m square divided by m square a square plus b square. Okay, there are a few steps. Okay, do it. There are a few steps, you just do it. Okay, it's just a matter of solving. You solve, you have the equation minus mgb a square plus b square whole raised to minus 1 by 2 is equal to minus mg. Okay, because you can now take this delta b away. All right, whatever multiplied delta b have to be equal. All right, otherwise you should choose delta b equal to 0, etc., which we don't do. Okay, so that's that. So b will be equal to, you will see that it's equal to, you can just solve this, and since there's a b here also, right, you have to bring it together and rearrange it a little bit, and the final result, I'll give you the final result, it's ma divided by m square minus m square whole raised to 1 by 2. That would be the answer. That would be the final answer. You can just check that. All right, if I have made any mistake, you can just check that. Now this is not very difficult. All right, I'll just explain. I'll just walk you through the steps that we have followed so far. Okay, we have got, we start with the principle of virtual work. Okay, which is summation over I fi a dot delta I vector equal to 0. Okay, in this case we have got two objects, so mg delta x plus mg delta b equal to 0. Now this is the equation that describes the equilibrium. Okay, as we said, delta x and delta b are not independent, they are connected by this constraint. They are connected by this constraint which says that the string is inextensible, the length does not change. Okay. You take the virtual displacement delta on both sides. You should remember that delta acts like a derivative, so you just do that and you can find delta x in terms of delta b. Okay, now you substitute it back, and since delta b is arbitrary, okay, this equation reduces to minus mgb a square plus b square whole raised to minus 1 by 2 is equal to minus mg. Now you just solve it for b and you get the final answer. Okay, now remember a is this length. Okay, it's not any acceleration, it's just this length. Okay, now this is such problems can be asked. Okay, because this principle of virtual work is part of our syllabus, you may be asked to solve a problem using principle of virtual work. It's not very difficult. You just write down the virtual work principle, the equation, and see what you can do, and normally the problem will tell you what to do. Okay, now with that I think I can conclude today's class. Thank you for listening, and we'll continue with more problems from Lagrangian mechanics in the next class. Okay, thank you.